Welcome back. This is the second of two lectures on the hydrologic cycle. We are going to discuss why atmospheric and oceanic circulation on Earth looks the way it does. Let's get started. First, a quick reminder of how the hydrologic cycle connects all the water on Earth. The hydrologic cycle involves the continuous circulation of water in the Earth atmosphere system. It is also known as the water cycle or the evaporation-condensation cycle. At its core, the water cycle is the motion of water from the ground to the atmosphere and back again via phase changes, and it's driven by heat from solar energy. The cycling of water happens locally or regionally within a watershed as pictured, and also globally via convection cells and atmospheric rivers. There are many elements that we are not covering, like snow and snowmelt and groundwater storage and movement, just due to lack of time. The main factors that affect wind and ocean currents are pressure differences and also the rotation of the Earth and Coriolis effect. Surface ocean currents are shown on the left. The currents that move warm water from the equator to higher latitudes are shown in red, and the currents that move cool water from high to low latitudes are shown in blue. On the right are atmospheric convection cells in blue and major surface winds in red. We will see many different versions of this image throughout this lecture, and that is intentional, as atmospheric circulation can be a little complex and different images click for different people. Let's talk more about how pressure differences and the rotation of the Earth affect wind and ocean currents now. The first way that pressure affects the Earth system is through the horizontal pressure gradient force. This is the change in pressure over the change in horizontal distance. These pressure differences tend to be small, subtle changes, but they can still cause strong winds. The map is showing a high-pressure area near the Great Lakes and a low-pressure area in the Rockies. That causes wind to rush from the high-pressure area to the low-pressure area. Horizontal pressure gradients can also be a factor for liquids. Next up is the Coriolis effect, which has to do with Earth's rotation and the fact that the Earth is a globe. Because the Earth is spherical, objects at the equator have to move faster than objects at higher latitudes. The Coriolis effect deflects objects, that is, it causes a longitudinal shift when objects move from one latitude to another. The change in latitude has to be pretty large in order for the Coriolis effect to be noticeable, though. It deflects objects to the right in the northern hemisphere and to the left in the southern hemisphere. You have to use the object's point of reference, though. Let's look at the northern hemisphere first. The red arrow is deflected to the right as the object is traveling to higher latitudes, and the green arrow is also deflected to the right when it is traveling to lower latitudes. Again, you have to use the object's point of reference. You can see that in the southern hemisphere, both objects are deflected to the left. I know the Coriolis effect can be a little confusing to wrap your head around at first, so here are some helpful videos if you need some extra explanation. Here is another view of atmospheric circulation. It shows the convection cells and surface winds. In the convection cells, rising hot air is shown in red and descending cool air is shown in blue. Uneven heating by the sun causes zones or bands of alternating high and low surface atmospheric pressure on Earth. Equatorial regions are hotter, so the air ascends, and there is a zone of low pressure that air masses from higher latitude comes in to fill. That completes the convection cell, and it is what creates the trade winds, which can be seen traveling toward the equator. Really, it is the resulting pressure gradients combined with the Coriolis effect that creates global wind patterns. You can see that the trade winds don't travel straight to the equator, they are deflected to the right in the northern hemisphere and to the left in the southern hemisphere. The presence of continents also affects things. We talked about maritime and continental climates in the last lecture. This is another view of atmospheric circulation that shows the surface winds more clearly. Surface winds originate in areas of high pressure and flow to areas of low pressure. So they originate in areas where air descends back towards the Earth and travel to latitudes where air ascends. And of course they are affected by the Coriolis effect. Just to prove to you how integral the rotation of the Earth and the Coriolis effect are to atmospheric circulation, here's what atmospheric circulation would probably look like on a non-rotating Earth. Air would rise at the equator and sink at the poles. This creates a single convection cell within each hemisphere. The prevailing winds moving over the Earth's surface would blow from the poles towards the equator in both hemispheres. You can see that they are not deflected like they actually are on our rotating planet. The convection cells that go from the equator to either 30 degrees north or south latitude are known as Hadley cells, and the area near the equator where the two convection cells meet is called the Intertropical Convergence Zone, or ITCZ for short. The ITCZ is, therefore, the area where the trade winds from each hemisphere converge, and it actually moves around a little bit. It is further north in the northern hemisphere summer because land heats up more than water. Remember that the ocean moderates climate. Now we're going to talk about geostropic balance. This is a factor for both air and ocean currents. Note that we typically call air currents wind. Geostropic balance is the balance between the horizontal pressure gradient that we learned about at the beginning of the lecture and the Coriolis effect. This balance determines the direction of large-scale winds and currents on Earth, and which way storm systems spin in each hemisphere. The image to the right shows the geostropic balance for an ocean system. There is an area of high pressure where the water is higher and an area of lower pressure. So the horizontal pressure gradient is going to cause water to flow from the high pressure area to the low pressure area, but it will be deflected by the Coriolis effect. The balance between these two effects causes the water to flow a different direction than either singular effect would if acting alone. Geostropic balance is really important in the creation of cyclonic and anticyclonic eddies, which are circular ocean currents, or storms, which occur in the atmosphere. When you have a low pressure area for either the ocean or the atmosphere, you will have cyclonic flow. That is shown on the far right for the northern hemisphere. That low pressure system means that water or air will rush in, but it will be deflected by the Coriolis effect, and that causes the eddy or storm to rotate counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. When you have a high pressure system for either the ocean or atmosphere, you will have anticyclonic flow. This is shown on the left for the northern hemisphere. That high pressure system means that water or air will pour out, but it will be deflected by the Coriolis effect, and that causes the eddy or storm to rotate clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. So let's look at that cyclonic flow again via an aerial view of a storm system to really show how the rotation gets set up. Remember that in the northern hemisphere, areas of low pressure, which is pictured to the right, create cyclonic or counterclockwise rotation because air rushes in to fill the void of low pressure. And that air is affected by the Coriolis effect, which deflects all incoming air to the right in the northern hemisphere. This is shown by the red arrows on the image. That means the actual storm system rotates to the left or counterclockwise, shown by the black arrow in the image. Conversely, an area of high pressure causes flow in the opposite direction because air is leaving the area of high pressure and is affected by the Coriolis effect. Most massive storms are associated with low pressure systems, or cyclonic flow. Here are some tropical storms from September 2019. While the rotation is hard to see for some of them, two of them are quite obvious. The one off the coast of Mexico and the one off the east coast of the US are both clearly rotating counterclockwise, and since this is in the northern hemisphere, that tells us these are low pressure systems. Let's talk about storms a little more because I'm sure you have heard of various newsworthy storms before this. There are a lot of terms that get thrown around for storms, and it can get kind of confusing. Hurricanes and typhoons are the same weather phenomenon, tropical cyclones. Recall that a cyclone is a storm or system of winds that rotates around a center of low atmospheric pressure. And remember that this is the opposite situation of an anticyclone, which is a system of winds that rotates around a center of high atmospheric pressure. There are distinctive weather patterns associated with both cyclones and anticyclones. Cyclones, commonly known as lows, generally are indicators of rain, clouds, and other forms of bad weather, so it makes sense that hurricanes and typhoons are cyclones. Anticyclones, commonly known as highs, are typically predictors of fair weather. In the North Atlantic, Central Pacific, and Eastern North Pacific, the term hurricane is used for lows. The same type of disturbance in the Northwest Pacific is called a typhoon. Meanwhile, in the South Pacific and Indian Ocean, the generic term tropical cyclone is used, regardless of the strength of the wind associated with the weather system. But what causes cyclones? Well, when the surface water is warm, the storm sucks up heat energy from the water. That is why they form close to the equator, as seen on the map of major tropical cyclone zones and their typical paths. This creates moisture in the air. If wind conditions are right, the storm gets big enough and becomes a hurricane. The warmer the water, the more moisture there is going to be in the air. This translates to bigger potential for stronger hurricanes, meaning that strong cyclones are a climate change effect. I highly recommend checking out these links if you want to further review global circulation, the Coriolis effect, or check out winds in real time. I actually captured an image for winds on July 11th, 2022. It's a pretty neat interactive globe that is fun to play around with. Let's zone in on general circulation of the ocean now. There are 5 large subtropical gyres, the large circular current systems you see in each ocean basin. The North and South Pacific gyres, the North and South Atlantic gyres, and the Indian Ocean gyre. The main equatorial currents travel west. Earth turns to the east and winds drive these currents westward. The western boundary currents, which are on the eastern sides of continents, carry warm water to higher latitudes. Then the eastern boundary currents, which are on the western sides of continents, carry cold water to lower latitudes. So why do they form these giant circular gyres? Well, the equatorial currents are deflected to higher latitudes by running into continents. The Coriolis effect doesn't actually have any effect at the equator. Then western boundary currents, which are on the eastern sides of continents, are deflected to the east by the Coriolis effect. High latitude currents are then deflected to lower latitudes by a mixture of the Coriolis effect and continents. Finally, eastern boundary currents on the western sides of continents are deflected to the west by the Coriolis effect. This causes western and eastern boundary currents to be super different. Western boundary currents are warm, narrow, deep, and strong. This is a function of the water at the equator being deflected poleward all at once. And of course, they are warm because the water was recently at the equator where there is higher solar heating. Conversely, eastern boundary currents are cold, broad, shallow, and weak. This is a function of the Coriolis effect forming the current. It doesn't affect the water as abruptly as being deflected by a physical object like a continent. And of course, these currents are cold because the water was recently near the poles. Note how the different boundary types lead to a steeper ocean surface slope on the western side of a gyre. This translates into a faster geostropic flow on that side of the gyre, and this reinforces the western boundary current characteristics. The Gulf Stream is a western boundary current for the Atlantic Ocean. It runs along the east coast of the US. This picture is showing sea surface temperature, and you can clearly see the Gulf Stream delivering warm water to higher latitudes. The actual current meanders a little, and you can see eddies break off from time to time, forming either cyclonic or anticyclonic systems, but overall it's a typical strong, deep, narrow western boundary current that delivers warm equatorial water to higher latitudes. Now we're going to talk about Walker circulation, which is an interaction of air and sea circulation. Walker circulation, also known as the Walker cell, is the airflow within the troposphere of the tropics of the Pacific Ocean. Parcels of air follow a closed circulation pattern in which air rises in the western Pacific and descends in the eastern Pacific. Walker circulation is caused by the pressure gradient force that results from a high pressure system over the eastern Pacific Ocean and a low pressure system over Indonesia in the western Pacific. The western side of the equatorial Pacific is characterized by warm, wet, low pressure conditions as the rising air masses condense and dump water out. The eastern Pacific is the opposite. It is defined by cool, dry, high pressure conditions. Walker circulation also causes an upwelling of cold, deep seawater in the eastern Pacific because water is being transported westward by all the wind, and deep water upwells to take its place. This cools the sea surface in the eastern Pacific and makes for a productive fishery because cold deep water typically has lots of nutrients. Next, we're going to talk about something called El Niño Southern Oscillation, which is defined by a certain mode of Walker circulation. Walker circulation is actually the atmospheric portion that controls El Niño events. An El Niño Southern Oscillation occurs when Walker circulation decreases or stops. Remember, El Niño describes the oceanic part of what goes on, while Walker circulation describes the atmospheric part of what goes on. And during El Niño, Walker circulation is temporarily halted. The impaired or inhibited Walker circulation causes the ocean surface to warm in the eastern Pacific because winds are no longer pushing water westward. The area of atmospheric low pressure starts to migrate eastward, and ocean currents follow. This causes warm water to pile up in the eastern tropical Pacific and causes downwelling. This kills the local fishery during El Niño events. The opposite situation also occurs, with a significant increase in water circulation. This causes an event known as La Niña, by intensifying the upwelling of cold, deep water in the eastern Pacific. It is basically an overcorrection of normal conditions, that is to say, normal water circulation. In the graphics, I have both La Niña conditions and normal conditions shown. You can see they are pretty similar, but there is definitely more upwelling of deep water in the eastern Pacific near Central America that would exist below the thermocline during the La Niña events. El Niño and La Niña, and the atmospheric conditions that accompany them, affect more than just the Pacific, though. You can see that large regions of the U.S. experience changes to weather. Land masses on the other side of the Pacific are also impacted, just not shown with these images. We are used to thinking about El Niño conditions on the eastern side of the Pacific, and there is a lot of rain in these areas, but countries on the western tropical Pacific, over near Indonesia and Australia, become extremely dry, and fires are common during El Niño events. The last topic we're going to talk about in this lecture is called thermohaline circulation, or the ocean conveyor belt. This is how deep water is transported around the globe. So far, we have really just talked about surface currents and then briefly mentioned upwelling of deep water, but that's it. But the ocean is extremely deep. There are vertical gradients in the ocean. Light decreases with depth, temperature decreases with depth, pressure increases with depth, and so on. There are layers to the ocean based on density. Density is the amount of mass a material contains given a volume of space. Denser layers sink, and different water masses of different densities don't like to mix. Water density is a function of two main things, temperature and salinity. With temperature, the colder the water, the denser the water. I put some images in of temperature profiles with depth for the tropics, mid-latitudes, and polar regions in the ocean. You can see that surface water in the tropics is much warmer than deep water because the sun is able to heat the surface. This effect is still present but not as dramatic at mid-latitudes. There is more seasonality at mid-latitudes as well. Then the poles are really cold top to bottom. There is still a seasonal effect, but that water is pretty cold year-round. The other factor is salinity. The saltier the water, the denser it is. Water is typically saltier in high-latitude environments because ice exudes salt when it forms, and because there is evaporative cooling of water traveling poleward. Water evaporates, but salt doesn't. When water becomes cold and salty, it gets denser and it will want to sink. So water that is cooled and the salt content is increased forms deep water. This image shows a profile of the entire Atlantic Ocean, both the northern and the southern basins. If you want to look at the cruise track that the research ship took, you can look at the bottom right corner. Back to the profile. Areas near the North Pole, or Arctic, are on the right, and areas near the South Pole, or Antarctic, are on the left, with the equator toward the middle, where it says 0 degrees north. The top layer consists of the surface currents that we have already learned about. They are pushed around by wind and affected by the Coriolis effect. AIW means intermediate water. Some layers form in the Antarctic, and some form in the Arctic. The layer that is visualized here formed in the Antarctic. NADW means North Atlantic deep water. It forms in the North Atlantic, and evaporative cooling makes the water very cold and very salty by the time it reaches the area where it sinks. ABW means Antarctic bottom water. The water forms in the Antarctic when sea ice forms and exudes the salt. The remaining water is very cold and very salty. It is the densest, and it sinks to the very bottom of the ocean. Once deep water forms, it follows a long circuitous route around the globe. Movement is very slow. It takes about 1,000 years. From this map, you can see that deep water is formed in the North Atlantic Ocean and near Antarctica. Then, deep water upwells in the North Pacific Ocean and in the Indian Ocean. Thermohaline circulation has implications for local ecology and atmospheric gases. Water that upwells is very cold, has high nutrients, higher CO2, lower pH, and lower oxygen, since microbes have been respiring organic matter the entire time the water was out of contact with the atmosphere. Deep water that forms takes the gases that it had at the surface down to the deep with it, including CO2. It carries the atmospheric signature of the time it formed. Obviously, that doesn't mean that gases won't change. Respiration will use up oxygen and produce CO2 the entire time it's out of contact with the atmosphere, but the oxygen will not be replenished for the entire time it is out of contact with the atmosphere. Of note is the fact that the ocean conveyor belt is slowing down. It's powered by the formation of cold, salty water. It's a conveyor belt. And climate change is making the water a little less cold. The speed has changed and stopped according to paleoclimate records as well, so this isn't unprecedented. This has far-reaching implications for the Earth system. Water that upwells will have more CO2, less oxygen, and have a lower pH if it's out of contact with the atmosphere for a longer period of time. Additionally, the formation of deep water helps to remove some CO2 from the atmosphere for a very long period of time. If this happens at a slower rate, then there will be a positive feedback for climate change. That concludes the material. Let's go through and review the main points. Uneven heating by the sun causes pressure differences in the atmosphere in the horizontal direction. This creates winds and creates storms. The Coriolis effect affects surface winds and ocean currents. It moves objects to the right in the northern hemisphere and to the left in the southern hemisphere. Earth's global atmospheric circulation consists of 3 large circulation cells in each hemisphere, which occur due to atmospheric pressure, the rotation of the Earth, and the Coriolis effect. They set up prevailing winds and precipitation patterns. Geostropic balance is a balance between the horizontal pressure gradient force and the Coriolis effect. It explains the direction of large-scale winds and currents on Earth. It also explains the sense of rotation of large, low, or cyclonic, and high anticyclonic pressure systems in each hemisphere. Surface ocean currents are driven by wind, the rotation of the Earth, the position of continents, and the Coriolis effect. ENSO is a prime example of how the atmosphere and ocean are linked, with normal Walker circulation conditions leading to upwelling in the eastern Pacific and a weakening leading to El Niño events. ENSO affects weather patterns well beyond the tropics, though. Thermohaline circulation is an important aspect of ocean circulation, and deep water is formed in areas of the ocean where water gets cold and salty, setting up the ocean conveyor belt. The slowing or stopping of the ocean conveyor belt will have far-reaching consequences for the Earth system. Thanks for sitting through the lecture. To test your learning, I suggest you review the material and make sure you can answer these questions.